I'm Jojo Joseph, a student of Rajgiri School of Engineering, and this is my assignment for RTOS. Let me introduce to the PIC microcontroller. PIC microcontroller is a very popular chip. It comes with in this assignment, we will brief on the architecture, the PIC microcontroller family, the software requirement, the hardware requirement for the PIC microcontroller, and programming. PIC has four families, which can be identified with their numerical representation. What's inside a PIC? PIC has an inbuilt CPU, I/O ports, memory organization, AD analog to digital converters, timers, counters, interrupt, serial communications, I2C communication, SPI communication, and there's something called a CCP mode, which we will come to understand later during this video. Here is a general representation of the CPU architecture in a block diagram representation. We'll start with central processing unit. CPU consists of arithmetic, logic, and memory operations as handled by the CPU. It is the core functionality. Core aspects of a CPU is the arithmetic logic unit, which handles all the logical decisions, and the memory units, which is where the memories of the microcontrollers are. And there is also a control unit which act as a communication bus with the CPU and other peripherals. Let's get started with the programming memory inside the PIC microcontroller. There is something called as PC, a program counter, which stores a command of the next instructions to be kilobytes of linear programming, addressing up to 120 bytes of linear data memory addressing. The RAM or registers. It's a volatile memory. There are two types of RAM registers inside a PIC microcontroller. One is general purpose registers, and another is a special purpose registers. The special purpose registers has 16-bit handling, data length, which is set, which functionalities is set at the time of manufacturing. Another is an electrically erasable programmable read-only memory where we store data. One advantage is it's non-volatile, so it's retain its data even when the IC is turned on. The data bus. There are data bus and address bus. Data bus is transfer and receive data, while the address bus is commonly used to transfer the address of the data that to be fetched. There are timers inside a PIC microcontroller, which we will use while trying to program it. Let me give you a brief idea on what timers are there in PIC microcontroller. As you can see, there are three timers, two of 8-bit and one 60-bit P scaler. There's a CCP option, capture, compare, and pulse width modulation, which help in generating the pulse width modulation signals, which is used in communications like SPI, I2, and UART. Another great advantage of a microcontroller is its I/O ports. Here in PIC microcontroller, there is 5 groups of output ports, namely port A, port B, port C, and port D and port E. These pins can be either set input output, and it is set based on TRIS registers. Changing the values of TRIS register, you can either put one of the ports in output mode or input mode. Apart from I/O operation, this particular pins have special functions like SPI, I2C, and interrupts, and PWM, pulse width modulation. Another great advantage of a PIC microcontroller is having inbuilt ADC. It has 10-bit 8-channel ADC. Another functionality you find in PIC microcontroller is two internal comparator. So you don't have to read them in the software. You can compare it directly. There are voltage reference modules, which gives out very precise voltage for reference applications available in these voltages. The clock oscillator. There are four internal oscillators, four clocks inside the PIC microcontroller. There's a 60 megahertz internal clock block, which is software selectable from a range of 16 megahertz to 31 kilohertz. 31 kilohertz is a low power internal oscillator. It has three external clock modes up to 20 megahertz, which is a fail-safe clock monitor, two-speed oscillation startup. Another special PIC microcontroller features are its operating voltage from the range of 2.3 volt to 5.5 volts. And while the PIC 16, the fourth family of PIC have a voltage range even much lower from 1.8 to 3.6 volt. It is a power on races, power on timers, low power brown up reset. These are the additional functionality associated with. Here for this assignment, we will be using PMP Lab Excite software to write code in C language, which will be converted into assembly language, and then to machine code in X. It's converted to X code, and this X code will simulate the circuitry in Proteus, and will run this C codes inside the PIC microcontroller in the Proteus to see how the program executes. We'll be doing three programs for this particular assignment. One, the very basic for any microcontroller, is blinking an LED using PIC microcontroller and simulating it in Proteus. This is a target circuit diagram. What we're going to do. Here's a crystal oscillator external, and we have connected. If you look closely, we can see that we have connected an LED to the pin 39 through a resistor of 230 ohms. So what we need for this particular assignment is PMP Lab ID, which we will use to compile the code for PIC microcontroller. And we also need here is a download file for the PIC MP Labs. We also need XC8 compiler to compile our C code into the machine language, converting it to the X file so that we can use that particular X code to run on the Proteus simulation. So let's get started. So once you have installed PMP Lab Excite, and we'll start with so once it's installed, we'll wait till it we'll give a couple of seconds to the software to boot up. While it is booting up, I'll brief you on what's our objective in this particular we have to write the code for. Um, Here is opening X Labs. You have to sign up with your username and password. Once done, you have to create a new project. Then you have to from the categories you have to take microchip embedded and take standalone projects. And once you've done that, you have to select PIC 16F1517, which is the microcontroller we're going to use in this particular uh, assignment. Click on next, and then you have to select the compiler. Here in this particular case, we're using X C8 compiler. Okay, the program has loaded. We'll wait for it to load. So once it's done, we'll create our new project. So here our new project has been created. We need to add a C main file, where we'll write this C code for uh, our particular application. Here it is being blinking off an LED. So see, right clicking on the source file will select new and add a C file, which we will edit later during the file. It will ask for CMIN. It has to be mentioned for our project. Well, let's call it blinked, since our aim is to blink an LED using PIC microcontroller. Now, once the ID opens with the source code for C, we have to write our program, which I will explain later during this video. Okay. And another is target window memory and configurations of bit. The PIC microcontroller has a lot of status bits which we need to configure, which is, for example, these are the external clock low power mode 0 to 5. These are the specific specific registers we have to specifically select before executing a code which changes the functionalities of the PIC microcontroller. These are the things like watchdog timer. How should there are different modes of operation. Here's watchdog timer, often is sleep, these kind of things, which I will explain later during the video. Once you have written the code for blinking an LED, you have to generate source code to output. The C file is converted. You have to select to output our codes will be generated to copy the rest of the program. Okay. Tris registers are the ones we use to set a port either as an input port or an output port. So here's the code. Include xc.h. Define crystal frequency. Specify the crystal frequency. Let's starting of the program. There's void main void. It doesn't return anything. Port D pin is as output. So our port D pin 0 is the output. So what we do is we mark that particular pin as output by tris D0. Tris is a register which either decides whether that particular port is an input or an output. Uh, Assigning it as to 0 indicates that that particular port is an output port. Initializing I. This is a variable that we're going to loop for the LED to blink. While 1. Look, it's an infinite loop. Uh, to turning an LED, we've connected our LED to port D. So RDO, RDO, which that particular register, we put it as 1, which in turn corresponds to that particular port, here port D, to be high. We delay for we then we have what we need is a delay. For that we use a continuous for loop, which increments the value of I from 1 to 999. And to turning the LED off, we again write onto the bit RDO the output of the D port to be 0, and we again add a delay for LED to stay turned off for a couple of seconds before it turning on. Again we write a for loop for that particular delay, and since it's a while loop, it's keep on looping for an infinite time. So once you've done this, we convert it into Xcode, and once we have successfully built our project and got an export, we copy this Xcode, which is you can file this Xcode in the directory of the project where you have saved. And now to simulate it, we will create the circuitry with the PIC microcontroller. We're using PIC food family, PIC 16F1517, and we add a crystal oscillator at a frequency of 2020 megahertz, 2 megahertz, I'm sorry, 2 megahertz, adding a couple of allied capacitor. Then we connect our RD0 port D0 pin to an LED through a resistor of 330 ohms. Copy and paste the Xcode into the PIC, the features of the PIC microcontroller inside the Proteus, and run the simulation. And you can see our LEDs blinking, turning on and turning off. We'll start with XP Labs right now. Here we're going to define our clock frequency. Define xt and frequency. It's 2 megahertz. Then we go to the void main. Void. Go top the different. We don't have to. Void main. Have to set the port D as 0. We have to change the address D0 is equal to 0. The trace register controls the input-output mode of the I/O ports. Then we initialize a variable I is equal to 0. Then we have to have a for-hour loop. So we design a while loop so that it will check. To turn the LED on RD0, it is to the I/O port to which we will be connecting our LED, and we need a delay. For that we have to we're writing a for loop. For I is equal to 1, I less than 1000, I plus plus. This will give us a delay based on the frequency and the number of instructions to be executed for executing a for loop, which writes a value of 5 from 0 to 999. Now we have to turn off the LED. For that you have to write TRDO is equal to 0. Then we have to wait another equal amount of time. We'll copy paste the delay code. Close the while loop. And this is a code. Then we'll run our build on this clicking on this particular button. Our program is successfully complete. Build. Then we go to the directory of this particular project, and here we can see the source file and the hex file. So here we can see our hex file here in this particular location. We copy this location. Copy. Now it is the time to create the simulation on Proteus. So let's get started on simulation with Proteus. So here you can see the rough circuit diagram for the PIC 16F1517 microcontroller. We have attached the crystal oscillator at 2 megahertz, and we have added two allied capacitors of 22 picofarads each, and we have added an LED to the RD0 through a resistor of 333 ohms. So here in Proteus, we select the PIC microcontroller. Now the other component we need is a crystal oscillator. We put crystal oscillator. We'll go with crystal oscillator. Crystal oscillator, we'll go with the quartz crystal. Okay. Okay, here's a crystal. We add it to the circuitry. And we attach the crystal to the clock out and clock. So let's zoom it. Okay. You connect the one end to the clock out. Okay, clock in. Clock in. The other pin to the clock out. Then we have the ground. Ground with here we can say okay. Here we write with capacitors of 22 picofarad. Ceramic of 22 picofarad. Okay. Alright. We have two capacitors. Copy and paste. Okay. To capacitor. Now we need a ground probe. Oscilloscope, DJ, current. What we need is a ground. Input output ground. So we try to find the ground. Terminals, ground pin. So attach it here. We connect each end of the one end, the other end to the capacitor. Okay. Alright. Now we need to add an LED. Here we write LED. So here So we're going to take a generic LED, red LED. Okay. So before that, we need our resistance of 330 ohm. 330 ohm. Okay, 330, which is okay. Resistance. We have 330 ohm. Okay, which we will attach it. It will be connected to RT0. Here we connect the RT0 to the resistor. Here we connect it to the LED. Positive, then maybe we add a ground. So we attach the ground. Okay. So here we go with here in the program file. What we will do is we'll go to desktop. There we'll go to dynamic. Okay, RTOS assignment. Okay. Okay, we need to go to the blink. For somewhere to stop. Hex code for that particular project is XP Labs. So here is the X file for that particular the program that we have written to blink the RT0 pin LED. We copy and paste its location from here. We click on it. Here there's a provision to add the here. So what we desktop. There's a file location. PC. User. Here's X file. We open it. Press. We press OK. Now here we're gonna run our program. So what we should do right now, so we're looking at what's issue. We have now page internet less error. Okay. The crystal is the issue, so we'll change it. We set the crystal frequency to 2 megahertz. Okay. When we run the program again, there are a couple of other errors. Okay. Let's see. What we'll do is here we'll 2 megahertz. Okay. Okay. So here you can see uh, a signal being sent to a particular. What we'll do is we'll attach a oscilloscope. Okay. We put an oscilloscope. We'll put an oscilloscope. We'll put it away. We'll run it again. So here we can see. Here you can see the LED turning off and turning on. That's just the time. So you can see the LED turning it off and turning on uh, after a particular delay. Similarly, we're gonna do the three more projects, which are similarly we're gonna do 3 more projects. So we completed our first project. Second one, we're going to use timers inside PIC modules to control the LED. So when you press one button, it jumps from one LED. It will turn on one particular port as high, then it will jump back. It will increment as another, and the last program is will be using the PWM controller of the PIC microcontroller. One new project. Microsoft standalone. Next, here we select a PIC 16 1517. Okay, here we'll go with the simulator. Next, we'll take the compiler. Project name is PIC2 timer 2 in PIC. The location of the project. We'll click finish. Okay. So here in the XP Labs we add our new main.c file. So here in this part we have to source file we have to write new text file. We have to go to main.c c folder. So here briefly I'll explain to the project. So these are the configuration spreads of the particular program. It is same as to the Blink program which we did earlier. Then include the header files, defining the crystal oscillator to 2 MHz. Then uh, void timer to delay. Here's a function which we will use to incorporate a delay. Here's a function which sends out a character corresponding to which the LEDs will be turned on. So after each time the LED is moved, the timer delay is executed. So here is the main program. We have defined TRISC0, that is the port C 0 pin has been defined as an input pin by adding it as 1. TRISD, uh, this instruction execute all the pins in port D to be 0. Uh, This registers to be 0, which corresponds or the pen as output. So here we have using a while input for creating an infinite loop. If RCDO is the port C pin 0 is connected to the micro switch. So when it is 0, that means the switch is not pressed. It calls a function called sequence 1, uh, and it sends a variable 1, and sequence 3, sequence 7, and sequence 15. So when this push button is pressed, RCDC 0, that is port C pin 0 is pressed is high, we define 4D pins, that is all LED pins to be turned off, turned on. So here's the timer delay functions. Before getting into that, I'll explain how we calculate the timer register value. So here it is. Here what we need 1 second delay. So we're going to calculate what is the value of the timer register to have a 1 second delay. So for calculation, we need our target is 1 second using timer 2. Timer 2 is an 8-bit and support 1:16 prescaler. Maximum delay is the delay is equal to 256 into prescaler into 4 divided by f oscillations is equal to 256 6 into 16. The prescaler 16 into 4 divided by 20 megahertz, our clock speed 20 megahertz gives us 819 microseconds. Now 500 microgenerator timers will be increment of counters. Okay, let's say 16, we end up with timer counter is equal to 100. So here the timer counter, by doing the calculations, we get the value to be 100 to have a 500 microseconds delay. So let's get back to the coding. So here is the timer delay function. Tcon2 timer 2 with the external frequency and 16 prescaler is added with a timer 2. From our calculations, we have found it to be 100. We have loaded that value 100. TMREIE is equal to 1. Enable timer interrupt bits clearly register. GI enable global interrupt. PEIE is equal to 1. Enable peripheral interface. For 500 seconds, we need to loop it for 2000 cycles to have. So for int I is equal to 1, we create a for loop for 2000 while timer after overflow. Turn on the timer after overflow. And here's how we do that particular. So right now what we're gonna do is click on build, which will create a X file for that particular project. So if we go to a MATLAB projects and timer, click on distribution default, production. So we'll wait for the production to complete. So once the build is successful, we go to the project file and copy the X file location. We copy the X file location. We place it in a draw case. MIPS Microcontrollers, and here we'll put. So we go to C user user MPL labs project time to distribution default function. Yeah, the hex file. Okay. For a particular requirement, we need to build a circuit. Uh, we need to connect an LED to all the port D pins. There are 8 port D pins, to each of which we will connect LEDs, and we'll connect the micro switch with a 10K pull-up to RCDO register. So right now we'll so copy to clipboard, paste. Paste from clipboard, paste from clipboard, paste from clipboard, paste from clipboard. So let's run the properties simply. Okay, now let's add. So now we have so what we do is we need to add. We'll add a push button. RC 0. So here's a first switch. So here we're going to write the code for using pulse width modulation on PIC microcontroller. So we'll have a new file. So let's explain how the pulse width modulation works. So uh, PWM is achieved using PIC 16 families C, CCP module or capture, compare and PWM module. This particular microcontroller has two CCP pins. One is CCP1, which is connected to RC2. Another is CCP2, which is connected to RC1. Each, each pin corresponding to a CCP register, which is CCP1 con and CCP2 con. So how PWM is achieved? There is a duty cycle and period associated with the PWM pulse width modulation signal. So PW duty cycle is equal to CPRXL CPX less than 5:4 divided by timer oscillation timer to prescale value into prescale value. So here's the period, uh, which is usually timer 2's preset value, and timer 2 is equal to duty cycle. So here's a code for creating the pulse width modulation. So we have defined the frequency to be 40 MHz. We have defined the timer 2 with preset 16, including XC compiler, including the pulse width modulation header file, void main, initialize pulse width modulation with 500 Hz with 50% duty cycle, and one that is CCP1 and start pulse width modulation 1 return. So what we're going to do is we're going to copy, we'll paste it and put the paragraph. Defining the clock frequency at 200, defining the timer preset 16, including the head file, including the pulse width modulation method name, or means initializing the pulse width modulation, starting the pulse width modulation tone, and we click on the build button. So here's the code for the pulse width modulation. We are defining as 20 megahertz, including the XC compiler, void main, PR to this particular value is done based on is based on our calculations. CCP one will converts to CPX is equal to that. Just our register is equal to say commas. So time this. Now we will. So for some reason our build is failing, we have to check it again. So we're connecting RC1 to the oscilloscope to see the pulse width modulation.